Okay, so now comes the last section, which is a stress strain relationship with an angle oriented laminate. Okay, it's a pretty heavy one, so therefore I don't know whether need to split out the video, but let's just continue and see how. Okay, and this starts from page 33 of your lecture notes part 2. Okay, and is related back, alright, to your this portion, page 26. Alright, and isotropic thin composite lamina, where the definitions of your Young modulus, shear modulus, Poisson ratio, alright, when they are the same or when they are equals are being described over here. Alright, you need to know all this. Alright, they are equal to each other, and because they are equal to each other, then you're gonna take in the numbers and plug it in into the equations that we're gonna discuss later. Alright, so therefore the page 26 is very important, and I think it's one of the main focus in the exam questions for calculations. Alright, so please take note of that. If you don't understand why the Young modulus, shear modulus, or the Poisson ratios are the same, or if you want to know more, you can go to V5.3, alright, and it's about the 3rd minute of the video, alright, which is somewhere over here. Okay. I think it's the 5th minute lah. Okay, it's about the 5th minute of the video. You can just take a look if you want to know more. And therefore, this allows us to start this unidirectional lamina, or n-isotropic lamina. Alright, or it's, in other words, only a certain direction. Alright, it's strong. In this direction is actually the strong one. In this direction is the weakest one. Okay, and therefore for a unidirectional with a certain angle, in this case, as you can see, alright, this is your so-called your system plane, alright, your reference axis, alright, x and y. But because of a certain angle, alright, this is actually your modulus of elasticity in this direction with a certain angle. Okay, and this is E2, alright, that is perpendicular to this E1. That is all it is. Alright, and the G1 are just your shearing, that's all. Nothing much, nothing special. Coming up next to this page, this is the page after this, alright, is a more detailed picture. Okay, previously was just this thing, alright. Now they are actually putting in a material. Okay, so this is the material, the shape of the material, alright, and you are orientating your fibers in this direction. That is all it's trying to say. And then this is the strength, the modulus of elasticity in this direction, and the modulus of elasticity in this direction. Okay, so this is another graphical view of this previous slide, which is this one. Okay, it's a more clearer view over here. Alright, and what it's trying to say is that it's important in this page is the area of face equals to dA. Alright, the area of face is actually this particular area, the shaded one that I'm looking at right now. Okay, because your stress is going to be applied in this direction. Okay, and stress is normally force over a certain perpendicular area, which is this plane over here. Okay, and therefore this is very important. And if you were to have a certain shearing in this plane, so in other words, you're going to shear this plane, alright, so this thing over here is like that. Alright, so if you were to try to shear in this form, okay, may somewhat looks like this. Okay, something like that. Okay, I don't know how to draw lah, but it's yeah, hard to draw. Your cube. Alright, so if you were to shear in this direction, imagine it's somewhat trying to break the your fiber in this direction. Right, it's somewhat gonna break it. Alright, so your fibers in the end may actually become like that. I don't know how to draw, but at least you get a point lah. Yeah, never mind, I'll give up. So over here, this is actually the same diagram we have just discussed, okay, but in a way that we're actually summing up the force in the fiber direction, alright, in this direction. Okay, And why do we want to do that? I also don't know. So let's see what's the result, and eventually we may know something. Okay, and therefore sigma 1 times dA is actually this plane. This is dA. Okay, so sigma 1 times dA comes from where? It comes from your force over your dA is equals to sigma 1. Alright, force over area is equals to your stress. And then if you were to bring out this area, this is what they are talking about, the forces. Okay, and over here, this is sigma x times dA cosine theta. So what is it all about? Okay, I would assume if you were to just take this piece out, alright, if you were to take this piece and translate it over here, okay, in this direction, this is actually your sigma x, correct? And then you have a certain angled plane, right? Your angle, that is this angle lah, okay, theta. Alright, so your stress in the x direction, okay, needs to be translated into this direction. So I repeat again, if you have certain stresses acting in the x direction, you have to translate it into this angled direction. Alright, and this is opposite, this is adjacent, this is hypotenuse. So therefore, if you think about it, if you translate this thing into this means is a over h, which is a cosine theta type of thing. Okay, so if I were to bring this h over here, what I will have is a is equals to cosine h cosine theta. Okay, so previously we said that the sigma 1 times dA is this one, right? So it is correct. Then we're going to talk about minus sigma x, because we are actually pulling in this direction, because your cube is something like this. Alright, your cube is actually that, okay? And then if you were to slice it into half, alright, this is your dA. We are looking at this dA position. So if you think about it, actually the forces trying to pull this cube apart is actually the outside one. You see, it's actually the outside one, the force this sided. Okay, and therefore we are actually looking at a minus. If you think about it, if I were to translate this thing into a bigger picture, our x direction, alright, is actually in this direction. Alright, this is sigma x. So it's actually going in the negative direction for this cube over here. Okay, you can likewise also have another form of the cube, which we have shown previously. Alright, it should be this one. Okay, but later on we'll talk about it. But this is a very deep topic already. So don't try to waste your time, but the main focus is this equation. Alright, you just apply your angle, alright, and it should be fine. Alright, and I think I'll just stop here, alright, because the main thing is just this transformation matrix, alright, where you transform a certain x. Alright, the x, just make sure that x is actually this x-axis and this y-axis, while your 1 and 2 is the laminate, alright, the angle of your laminate. Okay, and this is it. Or in other words, if you find it very troublesome or whatever, or very confusing, this is your x and y. Alright, so once you get your stress in the x, stress in the y, you will know what is the amount of stress acting in this direction, which is stress 1 and stress 2. Okay, which is what we are looking for. Alright, these two are the things that we are looking for. Okay, and therefore this particular matrix could help you with it. Alright, while to derive this equation, alright, I'll carry on now. Okay, so if you want to carry on, you can carry on to look at the derivations. Otherwise, I would suggest you can just skip this video and go on to the next slide. Go on to the next video then. Okay, and yeah. So the key thing to take note of this whole equation is the summation of forces. Alright, so at first, this portion over here is minus sigma x because you're pulling in this direction. Alright, so I'm gonna go into more details. Alright, so over here, this is your cube, as I say. Alright, and if you were to slice it into half, alright, this portion over here, this shaded portion, is the one we are looking at right now. Okay, and there will be a point, if you were to look into this thing, there will be a point where you pull in this direction, sigma x, or you pull at this surface, sigma x. So in this case, most likely we are pulling in the negative direction, so it's a minus sigma x and sigma x over here. I hope this is way too clear. Alright, if it's not, then I'm sorry about that. But anyway, you just need to know that, yeah lor. So you can just, if I were to draw it in a more manner, you see, so this is the sigma x, this is the minus sigma x. Alright, so this is why there is a minus sigma x. Okay, so if you want to talk about the forces now, so minus sigma x gonna multiply with a certain area. Alright, it can multiply with this area. This is the perpendicular area. Alright, your forces is always stress times your perpendicular area. Alright, so the perpendicular area, if you are to draw it out more clearer, alright, this is the area, and in order to find this area, this is the hypotenuse. Alright, where your angle is actually over here. This is your theta. Okay, this is super confusing. I took quite a while to actually think about it, and yes, finally. Okay, so over here, this is your global axis. Alright, or in other words, your x and y. Alright, and if you have to tilt this whole thing in a certain angle, okay, so this is your sigma 1, this is your sigma 2. Okay, this is your angle theta. Alright, over here, this is your angle theta also. Okay, if you think about it, if you were to bring in this direction, this thing will, this line over here will actually move in this direction also. Alright, so if I were to take this thing, alright, this is your, if I were to draw boldly, this is your sigma x minus sigma x, which is this one. Alright, and then, alright, this thing over here is your dA. Okay, this is your dA. Alright, because if you think about it now, if I were to draw like that, alright, this is your dA. Your area is at a certain angle, which is your theta, this theta, alright? And then over here, this is your adjacent, alright, the one that we are finding. Alright, because minus sigma x gonna multiply with its perpendicular area. Alright, so we are actually trying to find this area. Alright, and this is why A over H, alright, this is hypotenuse. Your dA is actually a hypotenuse, alright, which is equals to cosine theta. Alright, if so, your adjacent is equals to H cosine theta, while your H is your dA. Alright, dA cosine theta, which is why it's over here. Okay, and haven't finished. So this portion over here is only talking about the force in the x direction. Alright, so if you have a certain force in this direction, alright, then if you think about it, let me see. Oh my god. A lot of time wasted. Alright, this is your force x, alright, in the x direction. Okay, and if you were to draw all the way, alright, it took quite a long time to realize, link to here. Okay, this is the line of your force in the x direction, right? It's the same axis, and you will think about it, this theta now is not this theta anymore. You're actually looking at this theta, this angle. You get what I mean? Because I took quite a long time to think of this, so I don't know whether now am I saying the thing that is you understand or not. You know, I don't know whether am I saying the things that you understand. Alright, because there is a understanding gap now. Okay, because after knowing that, yeah, it's pretty clear. I think I'll just, if you know, then you can skip a few minutes later. Otherwise, you can continue to listen. Alright, so in order to get a full picture of things. So initially, this is in the sigma x, sigma y direction. Okay, and then if I were to tilt it with a certain angle, this will become sigma 1, right? This will become sigma 2, correct? This is the angle that is being tilted. Over here, this axis is tilted by this angle. Over here, this is tilted by this angle. Same thing, okay? And we say that we want to find the forces, which is the Fx. Alright, the Fx is actually going in this direction. Alright, minus Fx. Okay, so if you think about it, this is actually your opposite, this is your adjacent, this is your hypotenuse, where your hypotenuse is actually your dA. Alright, so we are actually keen to find stress times perpendicular distance. The perpendicular area is actually this one. Okay, or yeah, the stress times this perpendicular area. This is the perpendicular area. So therefore this thing over here, alright, is your adjacent. Alright, so adjacent divided by h is equals to cosine theta. So therefore adjacent is equals to h times cosine theta, where your h is your dA. Alright, and this is why you will have this fx over here. Okay, hopefully this is pretty clear. Now after knowing that your fx is in this direction, now we are going to look at translating your forces into the sigma 1 direction, which is this direction. Okay, and therefore this direction, you slightly extend this thing now, right? And you're gonna ignore what we have. You're gonna ignore what we have this thing over here, because what we are looking now is this full picture over here. Alright, you see, your force has become the hypotenuse of your sigma 1. Alright, it has become your hypotenuse of your sigma 1. Okay, and this is your theta angle. Okay, so if I were to draw this thing over here, then this is actually your angle. Okay, by the Pythagoras theorem. Alright, this is actually your angle. And therefore, if you have opposite, this is opposite of the angle, and A, this is adjacent. Maybe I should use this line. This line over here is your adjacent. Alright, so you want to find this line A, so therefore A over h again is equals to cosine theta. Alright, so A is equals to cosine theta times h, where your h is your force x, fx. So therefore fx times your cosine theta will give you this stress 1. Alright, so therefore we are expressing all of these forces in this stress 1 direction. Okay, in this stress 1 direction. And I believe after you know how to solve this thing, you should be able to also solve these things. Okay, because I'm a bit lazy to solve all this already. Alright, but the concept I would believe is the same. Maybe I should solve for the shear stresses also. Okay, so in order to solve for the shear stresses, I'll only solve for this part of the shear stress. Alright, after that I believe you also need you understand how to solve for this. Alright, this is for the sake of your future, if you need it. So this is the sigma x, sigma y again. Okay, and then we will have your maybe I should use a different color, sigma 1. This is your sigma 1, this is your sigma 2, this is the angle, this is the angle also. Okay, so there will be a shear xy. Shear xy meaning is shearing in this direction. Am I right? Okay, I think this, because there is two shear xy over here, you see, because the shearing are the same in the direction. But anyway, in this portion they are actually touching on the shearing in this direction. Alright, so you are trying to shear, yeah, they are talking about this portion over here. Alright, it's not this portion. This portion is shearing in this direction, this portion is shearing in this direction. So currently we are gonna talk about is shearing in this direction. Okay, because of this equation that I believe should be that form. Okay, so what we're gonna do, alright, is pretty straightforward. So we know that there will be a shear stress. A shear stress is acting in this direction. Sorry, the shear stress is acting negatively in this direction. Alright, so I'm gonna have this shear stress as tau xy multiplied by its parallel area. Alright, shear stress, the area is a parallel area. Okay, so this is your adjacent, this is your opposite. Alright, this is your hypotenuse, which is your dA. Alright, your dA. And therefore, your dA multiplied by cosine theta, alright, because A over h is equals to cosine theta. So if your h is equals to dA, as we say, your hypotenuse, you'll have dA cosine theta, alright, which is talking about this thing. Alright, and therefore this portion over here is actually your sheared area. Alright, so your shear stress multiplied by your sheared area, alright, is what we're trying to say. Okay, and therefore this thing over here, including the minus lah, okay, is actually your shear force. Alright, your shear force, I don't know how to write the shear force, but maybe shear force xy, I don't know, some shear force lah, okay. So shear force, we're going to translate into a direction in the same direction as this sigma 1. Alright, our purpose all along is trying to take this whole equation and sum them up in terms of this direction, in terms of this sigma 1 direction. Okay, I repeat again, this whole equations, our purpose is to sum them up in this sigma 1 direction. Okay, I hope this is pretty clear. And therefore, alright, your stress is in this direction right here. Okay, and you have this particular, and you are required to actually find this, maybe in this, in a blue color. Okay, you are required to find this, alright, this portion of the force. Alright, so since we know this thing, and this is the angle over here, alright, because of the hypotenuse area, so you know that in the z, this is in your secondary school lah, so angles over here is the same as angle over here lah. Okay, and therefore this is your O, this is your A. Alright, so we are trying to find your sigma 1, right? So your sigma 1 is actually your hypotenuse. So therefore, is it? I am wrong, but I would think that in the shear system, okay, your angle is something different. Alright, it's talking about here. This is your angle. Okay, surprisingly, alright, after thinking all along, I took quite a while also. So over here, this is your so-called your shear force. Alright, like acting in a negative direction, which is a hypotenuse, and this is opposite, this is adjacent, and you're actually finding this direction, right? You're finding this direction. We have this direction, so O over H is equals to sine theta. Alright, so therefore O is equals to H sine theta, where your H, or hypotenuse, is actually this thing now. Okay, this one. Okay, where hypotenuse is your this thing. So once you have your hypotenuse times your sine theta, you'll get this thing over here. Okay, so this is what they're trying to do all along. Okay, took quite a while, a lot of Pythagoras theorem, but the questions arise is that why don't I take this thing? Okay, I can also have this angle like that one. Then this thing over here is your theta. Alright, then I will have a different angle. Alright, I will have a certain other stuff. Maybe because, okay, I think it's, I know already. It's because if you think about it, alright, this is your opposite, this is your adjacent, this is your hypotenuse. Okay, so if you were to write in terms of the hypotenuse, because O over H is equals to sine theta. Okay, so if you were to write in terms of this, because in this case, this thing over here is your opposite. Alright, so therefore minus tau xy is equals divided by sine theta is equals to your H. Alright, your H is this one now. Alright, for example, if you think about it, trying to do in the fraction form is a troublesome thing. Alright, and therefore they actually translate into this form. Okay, which is this angle, and this becomes your hypotenuse instead of that. Okay, so this is a bit confusing here and there, but hopefully this is somewhat pretty clear because it's really cheap. But I hope this gives you a better understanding of all these equations, and I will believe, alright, the rest of the equations that is being shown over here, alright, are the same, of the same method of solving. Alright, you just need to manipulate your mindset into the Pythagoras theorem, so in order to derive the rest. I'll not go into details because the end in mind is actually to derive this so-called matrix. Alright, because actually this is more on the transformation matrix rather than a stiffness matrix. This thing over here is to transform your x and y direction, which is this x and this y direction into this direction. So in order to convert them using a certain angle, alright, with a certain angle, you need to have this equation in mind. Alright, and this is why we are deriving that. But actually it's not in your syllabus, but in the future if you need it, at least it's fairly useful for you. Therefore, this is it. In the next video we'll talk about how to apply the formula, I think, because over here should be the step-by-step thing to apply the formula. I don't know, so see you there then.